All right, guys. Thanks for coming again. Now, just a reminder. This is the. Let me see. I'm so sorry. Okay, I'm going to talk about what's coming up next week. Okay. I have sent out a reminder to all the people in the email list. So I'm not sure you all are in my email list, but anyhow, I'm going to let you know that remind you that next week, starting next week, from June 23rd to June 27th, which is a Tuesday to Saturday, that RCJ is hosting a Webots tutorial. And now, how is it different from what you have learned in the past few workshops? The main difference is this is going to be geared completely towards the RCJ game. So they are trying to use the Webot simulation as their potential replacement for the future simulation league. So then the content will, of course, the knowledge is knowledge. I mean, the knowledge you have learned so far definitely is applicable. Then, however, the content is going strictly pertaining to the RCJ maze game. And so then I highly recommend you should attend those meetings. And there are two separate time frames now. If you are familiar with Storming Robots site, you can easily go to Storming Robots. Now I'm going to go through it. So you go to Storming Robots and then look for simulation, or just scroll all the way to the bottom almost. So, which is right. Oh, I'm sorry, I'm not sharing screen. Let me share that screen. Okay, so you should always go to the Storming Robot site, and then you scroll over the bottom or just search simulation, right? And then you click on that, then you should get the link. Right, see, this is to sign up for the workshop. That's the daily plan. Now let's take a look at the daily plan here. The daily plan will be, let's say, this is the time. Now, of course, we have to use UTC because there will be people from all over the world there. So that you can sign up either time. Now, if you, by any chance, want to explore another platform, this is another time. So it's up to you, but then the Webot is these two times right here. And the 4 p.m., which is, that actually is 11 a.m. our time, they focus on just using Python. But if you want to stay with C and C++, then you need to attend the 8 o'clock meeting. Now, and then the content. On the 23rd, basically talk about basic stuff. And again, everything they talk about is good pertaining to the RCJ maze game. And 24th and 12th, every day we have a mini challenge for you to do. It's like, well, not so much a homework, but it's a mini challenge. They do recognition of the mini challenge. If they'll pick the best 3 and post it online so that everybody knows all the good work you have done. Your name on it, of course. And then on 26th, there's no meeting because on the 25th, they're going to give you a mini contest, which will be held on 27th. Now, again, the board is going to be very similar to the future RCJ games. So it's not Erebus field, okay? Then they will also talk about some more feedback sessions about what you should expect after that, because in September, at the end of the September, that is they call it demo competition around the world regarding using the RCJ maze game. So that's why I highly recommend you attend so that you get a much better information specifically pertaining to the game itself. Right? And then they have a RCJ forum you can get on to ask questions during the entire period of time. Actually, you can do it now, as a matter of fact. Okay, so then do sign up for their sessions. Okay, just don't forget, as a matter of fact, if you guys do that now, I'm going to give you the link on the chat. I'm going to say it on the chat right now. So everybody go ahead, sign up. Pick a time that you want, okay? Right there, I'll do it, everybody. Okay, everyone go to the chat. You should see the link, right? Please do go sign yourself up with the time that you want. Now, if you want to look at the VRAP, which is an entirely different platform, you need to go to the RCJ itself, okay, robocupjunior.org. You need to go to that if you want to explore another platform. Okay, so there are 2 platforms there. The one that you guys be using is called Webot. I hope that everybody knows by now. And then that's the long link, docs.google.com. That's the one you should go to sign up. But you want to go sign up for VRAP, you need to get the link. As a matter of fact, why don't I just help you guys find it? oops, right there. This is the rewrap, but then if you want to go to the another one, you need to go to robocopjunior.org, and yeah, the site has some problem here. So simulation. So this is this. You need to go here to sign up. If you want to use the rewrap, which is another simulation, then you need to go here. Okay. So I hope that that is clear. So rewrap goes there. Webot, you go here. So does anyone have any questions, first of all? Any hands? Actually, you can raise hand. No, no questions. Okay. Okay, all right. Okay, go ahead, Victor and Jeffrey, go ahead.
All right, so as a quick reminder, next week there won't be any webinar. So yeah, don't show up next week. Anyways, I'm gonna share my screen. So this week we're gonna talk about breadth first search, and we're gonna abbreviate it as BFS. So as a quick recap, last week we talked about mapping. And basically to map, we took this maze and we divided it into a whole bunch of different sections. And then for our map, we just used a simple array where each element of the array corresponded to a particular section in the maze. Then to store stuff in our maze, we just modified the element the element in the map that corresponded to the specific section in the maze. So if you recall, we needed mapping to do two things really. First one is we have to remember the wall arrangement of the sections that we've already been in. And we could do that already. So mapping took care of all of that because I can read the wall arrangement around me. I can modify my array accordingly. Then to access it, all I have to do is just access the particular element of the array of the section that I'm looking for. So wall arrangement is taken care of. The next thing we had to do, the next thing that mapping had to do for us was it had to enable us to find an efficient way around the maze. And while mapping allows us to remember which tiles we've been in, we still don't know how to find an efficient way around the maze. So what we're going to do is we're going to use sort of a greedy navigation algorithm where basically we're going to find whenever we hit, actually in all scenarios, we just want to travel to the closest unvisited tile using the shortest path. So let me show you what I mean. Let's pretend we're in this scenario where you have, let me hide this. Okay, there you go. So I have my robot right over here, this red dot, and then I have this blue section of all tiles that I've visited. So I've been to all these tiles, and I need to get to the closest tile that I have not been to using the shortest path. So if you count, it would just be this tile right over here, right? Because this tile is 3 tiles away, and this tile is only, this tile is 4 tiles away, and this tile is only 3 tiles away. So this is the closest tile that I have not been to. And also, we not only do we have to figure out that this is the closest tile that I've not been to, we also have to determine the shortest path is to the right, and to the right. We don't want to do any unnecessary paths. We go like up, right, down, right, because that just takes unnecessary time. So we need an algorithm to give us that this tile is the tile that we want to go to, and also the path to get there is just right, and then you're there. And that's what our breadth first search is going to do for us. So first off, I'm going to talk about breadth first search purely as an algorithm. And then after that, I'm going to talk about how it applies to the maze scenario. So before we talk about the algorithm itself, we need to go through a few concepts. The first concept is a tree. So what a breadth first search does is usually we can envision it as a graph or a tree. In this case, we're going to use a tree, sorry. So what breadth first search is going to do is it's going to start at the starting node, and then it's going to navigate all throughout the tree until it reaches the closest goal node and uses the shortest path to get there. That should sound familiar to what I said before. So it's going to start at the starting node, and you can see there are arrows. So I can travel from this starting node to 1, or I can travel from this starting node to 2. And then from 2, I can travel to either 4 or 5, and then etc. And then 4, I can travel to my goal node. So you'll notice that I have 2 goal nodes. I have goal node number 9, and I have goal node number 13. And goal node number 9 is 3 moves from the starting node. As you can see, I can go 1, 2, 3. Goal node number 13 is 4 moves away from the starting node. So starting node 1, 2, 3, 4. So goal node number 9 is obviously the closer one. So our breadth first search is going to start at our starting node, and he has to figure out that my closest node is 9, not 13, and the path to get there is 2, 4, 9. So some vocabulary. As I said before, a node is just one of these circle thingies, and it can travel from node to node. And then these arrows, we're going to call them edges for now. The terminology can kind of vary, but for our purposes, we're going to use an edge. So because you can start, an edge basically refers to a branch. And it's really called the tree because if you flip this entire thing upside down, you can think of this as the root of a tree. And then from there, a bunch of branches branch out from the starting node, just like a regular tree would. So that's kind of why it's called the tree. So, and these edges just mean I can move from the starting node to this node right here, as you can see by the arrow. So this is a tree, and then in a tree we have nodes and edges. So this is kind of the overall structure behind our breadth first search. Next, we're going to need to know what a queue is. So a queue is a data structure. So just like an array is a data structure, so is a queue. It holds values. For our purposes, it's going to be numbers. And if you think of a queue in real life, it's just like a line, right? The first people who get there are the first people in line, and that's how a queue basically works. So we're going to take numbers, and numbers enter the queue, like this 1 right here. So since this 1 was the first guy into the queue, he's going to be the first guy in line. We're going to call this first in, first out, right? So the first guy in is the first guy at the front of the line, and the first guy that goes out. Then 2 more numbers line up behind him. So we push in a 3 and we push in a -2. So right now, since we entered in the order 1, 3, -2, inside our queue, we have 1, 3, and -2. Then not only can we push numbers in, we can actually pop numbers out. So since 1 is at the front of the line because he got entered first, he's the first guy to come out. So we can pop him off kind of like this. So he comes out of the queue, and the queue is still just this box right here. And now 3 is at the front of the queue because 1 is now out of the queue. So then after that, we can continue just pushing and popping stuff in. So I can push in another 1. I can pop out another 3. And remember, these values, you don't have to worry about duplicates. So I can pass in like 5 1s, and then 5 1s will line up. So then I can keep pushing in numbers. I can keep popping out numbers. And the queue is going to be a fundamental data structure to our breadth first search, and we'll show you why. So when it comes to queues, there are 3 main functions that you have to know. So there's push, there's front, and pop, and they're all pretty simple. So what push does is I pass it a number, and it takes that number and it tosses it into the queue. So if I push in a number 2, let's say, then number 2 just goes to the back of the line. What front does is it returns the value at the front of the array, at the front of the queue. So in this scenario, if I call the front, it will just return a 3. What pop does is it just pops out the first value inside the queue out of the queue. So this just what I said before. Remember how this one got popped out of the queue? That would be what pop does. So I'm going to take a little bit and pause. So if you have any questions, make sure to alert the moderator or ask the moderator. So just take a few seconds, think it over. Hopefully you kind of understand. Okay, so we're going to continue. So now,
Hold on, Aditya actually asked a question.
okay, sure, yeah.
He asked, what's the difference between a queue and a one-dimensional array?
So the queue has this specific property that you can only access, or yeah, it has this specific property that whenever you push in an element, it goes to the front and they all line up in order. And then when you want to access the value, you can only access values from the front. So if I push in this 1, 3, and -2, they all go inside of order here. But whenever you want to access an element, you can grab the front element and you can actually pop it off. And actually, you can actually represent queues using a one-dimensional array. It's just that the first in, first out property, if I go in first, then I'm the first to come out. That's kind of the property that we want to use of a queue for our breadth first search. So I hope that answers the question.
If I may also interject.
Yeah.
Queues generally grow dynamically, right? Whereas
Yeah.
array, you have to give it a value, like the array is going to be, let's say, 20 in length. And as of course Jeffrey said everything else, but queues can normally grow dynamically. If you're implementing them in something like Robot C, that doesn't really work. But if you're implementing them in other languages like C++, yeah, generally speaking, they grow dynamically, and you can throw a lot of numbers into the queue. And you can also ask the queue how big it is, how many elements are inside of it at any one time. Okay, sorry.
Okay, so we're gonna have to remember this property where we push stuff in and the stuff at the front comes out. So we're gonna move on to our breadth first search.
Jeffrey,
Yeah.
so sorry. Another fellow asked, I think fellow guys, if you have questions, feel free really either raise your hand or type it up. If you feel like you have a hard time to type it fast enough, you can raise your hand. I would let you talk, so that, because this concept is very important to understand, and there are many ways to implement it. What Jeffrey said is one way. What Dennis said is also a little bit more embellished. So to some of you has been taking component class with us, to them makes a whole lot of sense, but then to some probably a little struggle there. So don't be afraid to ask questions. Now Isaiah, if I say your name right, he has a questions. Can you repeat the difference between pop and the front? So he needs to understand what you meant by the first in, first out concept.
Yes, absolutely. So what front does is it returns the value of the first element inside the queue. So you'll see that the first element in here is 3. If I call a front, this function is going to return the value 3, but this 3 does not get tossed out of the queue. It only returns the value of 3. If I call a pop, on the other hand, for the STLQ library, it does not return the front value. It just tosses it out of the queue, just like what you saw with this one. So once again, front returns the front value, but does not move anything out of the queue. Pop does not return anything, but it does move the front element out of the queue. All right, so since there were some questions, I'm going to take another few seconds, let you think it over.
All right, I think it's good. I don't think anyone else is asking questions. You can move on.
Okay, so as we said before, breadth first search is going to start at this starting node, and it's going to try and navigate through this tree, and it's going to try and find this goal number 9 and the path to get there. So to set it up, actually, there's something I forgot to mention before. So inside a tree, we have what's called parent-child relationships. And all that is if I say starting node is a parent, starting node's children are going to be 1 and 2 because 1 and 2 are directly below starting node. So 1 and 2 are going to be children of starting node. Similarly, 2 itself is also a parent of 4 and 5. And then 5 is also a parent of 10 and 11. So any node can be a parent unless, well, most nodes can be parents, so long as they lead to children below it, right? So you can think of parent is on the top, and then right below it is its children. So as you can see here, starting node is a parent, but it's not a child because it has no parent up here. And similarly, 16 is a child of 11 because 16 is below 11, but it's not a parent of anything. So those are parent-child relationships. So you have parent nodes and you have children nodes, and many nodes can be both. So to set up a breadth-first search, we need 3 main things. We need our queue, as you mentioned before, and then we have our current node. That's the node that we're currently be looking at. And then we have a parent-child array. And as you can see, this is just a standard array where I have the indices on the left, and then I have the values that they're storing on the right. So this is just a regular array. So this would be element 1 of the array storing a value of 0. This would be element 2 of an array storing a value of 0, and etc. So what this is the indices are going to represent children, and then on the values that they store, they're going to store the values of their parent. So as you can see over here, 11 is a child of node 5. So index 11, which is the child, is going to store its own parent, which is the 5, right? So as we navigate through the tree, you're going to see that we're going to mark parents for each children, right? So if we give another example, 2 is a child of the starting node. So eventually you'll see that 2, the value stored in element 2 is going to be its parent, which is the starting node, right? So these are the 3 main things we need for a breadth-first search. So let's start. To start things off, we're going to push in the starting node into the queue, like this. Remember how if I push it in, it goes to the front of the queue. Then we're going to mark start. It's going to correspond with start because start has no parent. So start is not a child of anything, so we're just going to mark it as start. So the first thing we do, the first step in a breadth-first search that we're going to loop over, because breadth-first search is actually the kind of 3 main things just looped over and over again. So the first part of that loop is we're going to take the first value of start, the first value of the queue, which is the front, and we're going to place it into the current node, and then we're going to pop it off the queue. So I see we have a question from Rohin. So if you want to, I guess, send it to the moderator.
Yes, I'm so sorry. I should have mentioned that again at the beginning. Everybody, if you have questions, send it to moderator. Do not send it directly to the instructor because they try to focus on their own talk, so they won't look at the chat. So you want someone to look at your chat as soon as possible, set it to the moderator, okay? Thank you.
Okay, so I guess I'll move on, but if it's worth interjecting, then I guess Ms. Elizabeth, you can stop me. Anyways, so as I said, the first step of the loop is we're going to take the front element of the queue and we're going to put it as our starting node, and then we're going to pop it off the queue. So like I said, we're going to take the first node, the first element inside of queue, set it as the starting node, and then pop it off. So now the queue is back to empty. The second step is we're going to look at our starting node and we're going to push all of its children into the queue. So as you can see, starting node branches off to nodes 1 and nodes 2. That means our breadth-first search is going to push 1 and 2 into the queue as such. So as you can see, once again, the starting node has 2 children and both children got pushed into the queue. then we're going to mark the parent-child relationships inside our parent-child array. So we found out that both 1 and 2 are children of the starting node. So remember, the indices, the numbers on the left, are the children, and the values that they store, which are on the right, are its parents. So 1 and 2 are children of start. So we're going to mark it as such. So 1 is a children of start, and 2 is also a child of start. And that is the kind of third step of our breadth first search. Then we just go back to looping the process over and over again. So if you recall, the first step is going to be taking the front element of the queue and putting it inside our starting node, and then we can toss it out of the queue. So start is replaced by 1 over here. Then we can take 1 out of the queue. Then our second step is going to be pushing in all the children of our current node into the queue. So 1 branches off to 3 and 3 only. So 3 is going to get tossed into the queue like this. Then we found out that 3 is a child of 1. So remember, the child is always on the left-hand side, the indice. So 3 is going to have a parent of 1 like this. And then we're going to loop it again. So we take the first element in our queue and we put it in our current node, 2, and then we pop it off the queue. So it's gone. Now 2 branches off to 4 and 5. So we're going to push 4 and 5 into the queue like this. Then we found out that 4 and 5 are both children of 2. So 4 and 5 are going to have 2 as their parent. And then we loop the process again. So I'm going to go a little bit faster. So pop 3 off the queue, then 3 branches off to 6 and 7. Then we found out that 6 and 7 are children of 3. So 6 and 7 correspond to 3. Then we do it again. Pop 4 off the queue. 4 corresponds to 8 and 9. So 8 and 9 go into the queue. And then we mark the parent-child relationships. So 8 and 9 are children to 4. So now we actually hit one of our goal nodes. And right there, we can actually stop our algorithm. So we say that, hey, 9 is a goal node, so I can pause for now. So as you can see, I only have one chunk of our parent-child array filled out. But that's perfectly fine, because as long as we can get to 9, we don't care about any of the other nodes for now. So if you want the path, you can think about the parent-child relationships. So to get to goal node number 9, we have to go through its parent, which is number 4. To get to number 4, we have to go through its parent, which is 2. To get to 2, we have to go through its parent, which is the starting node. And where did we store our parent-child relationships? Right here, right? So remember, we said to get to 9, we have to go through 4. So if we index element number 9, we see that, hey, we have to go through 4. So then we're going to jump back up to this element right here, because to get to 4, because 4 is the child, we have to go through its parent, which is 2. Then to get to 2, we have to go through its parent. So we go to where 2 is a child, which is the start. Then once we hit the start, we know we're finished. So our path goes start to 2 to 4 to 9. So all we were really doing is retracing our steps. So 9's parent is 4, then 4's parent is 2, and 2's parent is start. So our path goes start, 2, 4, 9. As you can see over here, start, 2, 4, 9. That's the shortest path to the closest unvisited, or our closest goal node for now. And the reason why breadth first search works is it basically checks level by level. So it starts at the very first level, the starting node, and it sees, hey, do I have any goal nodes? If not, then it moves down to the next level and checks this entire level. Hey, are there any goal nodes? If not, checks the next entire level, the 3, 4, 5 level, and says, hey, are there any goal nodes? If not, it keeps going. And then it moves along to the next level, and it says, hey, there is a goal node. So that's why it hit 9 before 13, because 9 is closer to the starting node because it's on a higher level than 13. So that's kind of the reason behind why breadth first search works. So once again, I'm gonna pause for a little bit. Make sure you ask any questions to the moderator, and yeah. So if you send any questions to me specifically, make sure, as Ms. Elizabeth said, send it to the moderator instead. So I'll just play it back one more time.
Jeffrey, may I well, based on my experience, then I think it may be, how about when you are moving on to add on the queue, ask everybody.
Okay.
Okay.
Okay, well, okay. So you have the start. So, well, I guess, well, start branches off to node. Oh. Well, okay, so I guess as we go through, I'll give you some time to think the next step. So first step is current node start. So then our next step is to put its children in the queue. So you can think about that real quick. So starts children are 1 and 2, as we said before. Then the next step would be to mark in our parent-child array, and we mark the parent-child relationships. So remember which are the children on the left or on the right. So think about that. So remember the children on the left and the parents are on the right. So then we mark 1 and 2 are children of start. Then we continue the process. So pop off 1, and 1 branches off 2, 3, and then the parent-child relationship is 3 comes from 1, and then let's continue the process. So I mean, unless there are actual questions, I guess we can move on, because we'll post a video of this later, so you can always go back to it if you're still a little confused.
Yeah, maybe just worth to go through it one more time and that's it. And
okay.
Ask questions.
Okay, so to start this off, we're gonna push in the starting node into the queue, and then start corresponds to start. So this is our starting position. So remember, our breadth first search is composed of 3 main steps. Step 1, pop off the front element of the queue and put it into our current node as such. Then our next step is going to push all the children of our current node into our queue. So all the nodes that our current node branches off to, which is 1 and 2, are going to get pushed into the queue. Then we're going to mark off the parent-child relationships inside our parent-child array. So 1 and 2 are children of start. So elements 1 and 2 are going to store the value of start. So that was our third step. So we go back to step 1, where we take the first element of the queue, pop it off, 1, and then we push its children, which is step 2, into the queue. So 1 is a parent of 3, so 3 is going to get tossed into the queue. Then 3 corresponds with 1 because 3 is a child of 1. And then we repeat the process again. So step 1, move the front node from here to here. Step 2, take all its children, 4 and 5, push it into the queue. And then step 3, mark off 4 and 5 are children. Go through the process a little quicker. So pop off 3, then 3 branches off to 6 and 7, then 6 and 7 are children of 3. Then pop off 4, 4 corresponds to, 4 leads to 8 and 9, and 8 and 9 are children of 4. Then right there, we hit a goal node, and then to retrace our steps, once again, this is just saying, in order to get to this node, I have to go through my parent. So I'm going to retrace my steps. So in order to get to 9, I have to go through 4. Then we find the element, then we find element number 4, because this is where we stored the parent of 4. So remember, element X is going to store the parent of node X. So if I'm looking for the parent of 4, all I have to do is access element number 4, and it'll give me my parent. So the parent of 9 is going to be 4. Then I access element 4, and then its parent is going to be 2. And then I access element 2 for the parent of 2, which is start. So once I hit start, I know I'm cool. So then from my retrace steps, I know it's start to 2, to 4, to 9. And that's my shortest path to the closest goal node. So, still have quite a bit to get through. So I'm going to pause for another like 5 seconds, and then I'm going to move on. All right, so now we're going to talk about applying the breadth research inside the maze scenario. So it's actually really all not that complicated. Each section, just how when we mapped, each section of the maze is going to correspond with a specific element of our map. So similarly for our breadth research, each section of our maze is going to correspond with a node in our tree. So, and the children of a particular node is just the adjacent tiles to a specific tile. So I'll show you what I mean. Let's say our robot is in this tile with the box right here. This tile, if we restrict ourselves to going north, east, south, or west, from here the robot has 2 options. It can go up, or it can go to the side. So we can think of this gray box as the starting node, and then its children are this node, this section right here, and this section right here. So we can call this, I guess, section number 1, and then this right here, section number 2. Right? Because starting node has to lead to these 2 nodes, and as you can see, this tile leads to this tile and this tile, right? From here, we can branch off to these 2 tiles, the 2 red tiles, right? Then, just like in breadth research, we pick one of the tiles, let's say it's this tile, and then this guy branches off. This guy branches off to this tile and this tile. So then, this gets pushed into the queue. And then, according to the order of breadth research, we're going to have to go to this red tile. And you can see that this guy branches off to this tile. And something important to note is that we don't want to redo these tiles, right? Because first of all, this is where we started off at. So there's no point in going back to it. And this guy's already investigated by this guy. So this red tile down here only has to worry about this green tile, not this yellow tile, because our breadth research has already made it there. And the way we can tell if our breadth research has already been to this tile is if it has a value in its parent-child array. Because if we've been to a specific tile, let's say this tile, inside our parent-child array, this guy will have a parent. So let's say this right here is section number 3, or node number 3. If we look back at our parent-child array, if we've gotten to this node in our breadth research, element number 3 will have a value of 1. So if we're trying to figure out whether or not we should go to a specific section, all we have to do is check if it has a parent. Then that means we already covered it. If it's not, like these, you can see that these sections we have not been to, right? So they all have an element, they all have a value of 0, right? So we know we've never been to element 13 because it has a 0 for a parent. Whereas we've been to all of these because they all have parents. right? So that's basically how you check whether or not your breadth first search has already been to it. So as you can see, this breadth first search is going to fan out, and then eventually it's going to hit the closest unvisited tile. And then it's going to return the path to the closest unvisited tile, right? And one last thing before I turn it over to Victor is, so our goal nodes inside our tree are going to be any unvisited tile that we've been. And remember, you can check if we've been to a node before in our map, because in our map, we're marking what tiles that we've been to, and we're marking and any tiles that we haven't been to. Remember, that visited bit that we talked about last week is going to be set to 0. So that's how you check for goal nodes. So basically, if I have been there, then it's a goal node. So during the error-based competition, you're also going to have to return to base. And it's actually really simple to return to base. Let's say my robot is in this section. All we have to do is start a regular breadth first search that fans out, but the only go node is your home base. So this is going to be the only node that you'll be satisfied with to end your breadth first search. So our breadth first search is going to fan out from this tile, so it's going to go and it's going to explore the maze. And then once this guy gets pushed into the queue, then you know that you're good. And then the breadth first search will do its thing and then return the path. So that's kind of the general idea of breadth first search. So I guess from there, we'll give you another like 5 seconds to ask any questions to the moderator, and then I'll turn it over to Victor. Okay, so one thing I should mention is before, if I go to the queue from before, we can actually call this, when we push stuff in, we can actually call it an NQ, and then when we take stuff out, we can actually call it DQ. It's just terminology, I guess. But the functions for the STLQ is still push, front, and pop. But it's just terminology might be different. So sometimes push is referred to as NQ, and then pop is referred to as DQ. So other than that, I guess, Victor, you want to take over?
All right, so Jeffrey talked about like the theory behind breadth first search. I'm going to talk more about the C++ implementation side of things. And I'm going to share screen. So I'll try to speed this up a bit because we actually are at like 10:45. So, all right, I have a sample program opened up here. And so first of all, the thing is that C++ already provides an implementation of queues in their STL. So you don't actually have to implement the data structure yourself. And before we talk about the breadth first search code, we're first going to like go over how to use the C++ queue. And the queue has the advantage, at least in C++, the STL queue has the advantage of generic types, where you can pretty much use like any type of variable or class. It could be user defined, anything you want. So for example, if I want like a queue to store integers, first thing I have to do is I have to include queue up here. And to create a queue of integers, I just say queue and then opening int, which is your data type. So whatever you want your queue to store goes in between these arrow brackets, and we can name it queue. Now, as Jeffrey said, you can push and pop with queues, so we can do the same thing. We can push onto we can push numbers into our queue, like for instance, number 1, and we can also pop. So the way we get what's at the front of the queue is with queue.front. And for instance, we only have a 1 in our queue right now. So if we print that, build that, reset, you'll notice that our queue does.
I'm sorry, Victor. I'm sorry, Vic, I don't
Yes.
mean to interrupt. You might want to just briefly explain what C out is, because some of these kids are coming straight from C, have not seen C++
Oh,
before.
okay. We've used cout before previously, so cout is pretty much the C++ equivalent to what you might find in C that you're probably used to for printf. And you'll notice it has a pretty weird syntax. All it is pretty much I type cout and then um, double opening tag. And this is what I want to print out, q.front. And then I have another one of these. And end L just means end line, which creates a new line. So it's equivalent to \n. And for instance, if I were to push multiple things onto my queue, so let's say I push 1 and then 2, and then let's say I pop, and then I print what's at the front again. We should expect exactly this, right? So we push the 1, so 1's at the start of the queue. We push 2, so 2's right behind it. We print 1, we pop, so 1 exits the queue, and then we print 2 now because that's now at the front of the queue. So that's C++ queues. And we use queues not only for our buffer search algorithm, but it's also useful for other cases as well. For instance, after we use our buffer search algorithm to find the next unvisited tile, we have like a list of directions we need to take in order to get to that unvisited tile, right? And that may involve going over many other previously visited tiles and possibly taking a lot of turns in a certain order. Now, if you'll remember, our controller has to repeatedly call this main while loop in order for the simulation to run, which means we have to save our directions somewhere while still being able to loop through the main loop. So a queue is like a pretty good data structure to use in this scenario because we essentially need a list of move forward and turn commands executed in a certain order. So the idea is we save all our commands into a queue and complete them one by one until we have no more commands remaining in the queue, which should mean we've reached the unvisited tile if our buffer search worked. And we're going to do that actually with something called a queue of functions. So we have functions for moving forward and turning. We're going to use a queue of functions. And this is going to demonstrate some pretty advanced usage of C++. So it's probably the first time you're seeing something like this. Don't worry, but it's something like really cool you can do within C++ in my opinion. So first things first, I'm going to include functional up here. And this C++ essentially allows you to treat functions as objects. And that may sound really strange, but you might have even seen this before because you can have like a function pointers and things like that. So if I want to make, for instance, a queue of functions, I can say queue, and then I can use function. And in this case, I'm referring it to as more of the class, not a regular function. And we have another bracket here, and we can say void commands. So here, this is going to look really weird, but I created a queue, and in here, it stores functions. The queue stores functions, and the queue is called commands. And what void means is that this just refers to the return type and parameters. The return type is void, and it takes no parameters. And now I can actually push and pop functions into my queue. And I have like a very basic function right here. It's just called add. It takes in 2 parameters. And the thing is though, our function, right? We said our queue is going to take in functions that are specifically a void return type and no parameters. Well, we have 2 parameters right here in our add function, so we can't directly push that back. But what we can do is we can use another function called, so if we push we can say bind add 1, 1. And bind is another function that you've probably never seen before. What bind does is it binds the arguments to a particular function. So for instance, I want to bind the add function with the arguments 1 and 1. And now you'll see in a second what that does once I do this. Commands front. Right. It prints 2. Why did it print 2? Because we bound 1 and 1 to our add function. And then what we did was we called commands.front. And so front, once again, gets the first element in the queue, which is literally our add function. And then we have a second pair of parentheses to call that function that we retrieved from the front of the queue. So this is going to look really weird. Like you don't see this something every day, right? But it's something really neat and handy that we used in our buffer search code because we have functions to move forward and turn. And the easiest way to save them is actually within this queue data structure. We just push them all on, and then as we call them, we pop them off. So, and I think Jeffrey, do you want to show the flowchart, or do we have time for that?
Perhaps then I think what we need to do is I think we need to kind of defer this because I think what you just went through is quite advanced. So looking at the list, I probably can spot 2 people. I know that they probably follow through what you said, but then the rest probably a little too much. So I think it would be good that I think we are planning to have another talk to go into a little bit more advanced topics. And what Victor has expressed that the implementation is a little more optimal, and often that to implement something optimal actually is a lot more difficult to understand. So we are planning to have another talk to digging more in depth as if how to make this a more optimal solution. I think that will be better because it's almost an hour already. So I think we should wrap that up. Now, so do you feel like you need to add in anything, guys? Jeffrey, Victor?
No.
No? Okay, good. So what I'm going to, Jeffrey, I think you mute yourself. I saw you talking, but you're not talking. Right, okay, so what I'm going to do, keep an eye open on more notification. We're going to definitely add on another talk, which going more in depth in terms of the more optimal solution and how to implement it. And bear in mind that do go online to sign up for the workshop next week. You do have options for 2 different time frame. One is 8 o'clock at the evening. Another one is 11 a.m. The 11 a.m. is being hosted by the UK team, and then the 8 p.m. is going to by Victor and Jeffrey also. However, all the content is going to specifically pertaining to the RCJ Maze Simulation League, and then they're going to host a demo competition worldwide in September, like late September. So of course, more details is going to be released. The RCJ team has been working very diligently, and then every week, like twice a week or 3 times a week meeting to get these things going so that keep everybody busy. And in September, that should be a lot of fun, challenging fun, of course. But do keep in mind that I do put out the 2 links to everybody to sign up. And so I'm going to put that out again. Please do that, go in there and then sign up pick up a time that work for you, okay? I'll put it out again. All right, yeah, and also in the link that will be in this website right there. I mean, you can go to our website. That's where there is the center, which you get all the links that you want. And there will be a link to the forum that you can continuously ask questions to the RCJ World community, and also any new notification as well. So do keep that in mind and mark that as your Oh, I'm so sorry. The link is just not working. Not working. The copy and paste not working. That's kind of annoying. I copy and paste wrong stuff. Sorry about that. I'm gonna write that up. Webot.html. So I'm gonna put the link out there again. Where is this? Right there. Okay, just go to that link. You see everything. Okay, so you see all the link, and do sign up for the Webot workshop next week. You don't have to attend every one of them because they always have a recording anyway. Okay, and more importantly, sign up to the RCJ forums. That's where all the experts are going to be there to answer your questions. Okay, all right, very good. I think we'll wrap that up. Thank you very much, Jeffrey and Victor, and then everybody else. And hopefully I'll see you at next week meetings and then even at the demo competition. Okay, have a very good day. Take care. Bye-bye.